Today is November 10th of November 2024, and we will do calculus for the boundedness, primum, and what is infimum. And we will talk about what is least upper bound, and we will also talk about well-ordering principles and relationship of mathematical induction, and Archimedean property, which is one of the most important property in real number. I will get started. First, this is intermediate value theorem that we see again and again. The most important thing in the intermediate value theorem is if it is continuous function and if it is real function, then there will be, if you set the A and B, then there will be, if FA and FB has different sign, then there will be some point that satisfy FC equals to 0. And there's a lot of things that you should think about. There are many people define analysis differently, but some people say analysis is treating real number, and some people say analysis is learning function. There's some Weierstrass function which is continuous in every interval, but there's nowhere is differentiable. For this is kind of nice function. This is continuous function. So some people say analysis is studying the subject that study function. Let's go real quick. This is how natural numbers are, and integers, rationals, real numbers, complex numbers. We should actually rigorously define these numbers, but I will just pass it. But there's something that we should think about here, that natural number and integer has same cardinality. Jonathan, maybe can you do the proof why the cardinality between N and G are the same?
So not a super rigorous proof, um, but as an example,
You
for
you can maybe give an idea
the
or intuition or
yeah, so them having the same cardinality means you can assign each integer or each natural number to a unique integer and vice versa.
Mhm.
And one of the ways to do this is um, so how to explain this? So for every even or for every positive integer, map it to an even natural number.
Mm.
Um, so map 0 to 1, and then +1 to 2, +2 to 4, and so on and so forth. -1 to 1, -2 to 3, and so on and so forth that way.
Mhm.
Um, that's not really a proof, but that's the general idea of what you're going to need to do.
Okay. Yeah, this is how we map.
Generally, you would go the other way, going from the natural numbers to the integers, but
Okay. Okay, that's how it goes. And then lift upper bound property came out. Lift upper bound is let S be a non-empty set of R, then there will be set which is bounded above. If some beta is it's also element of real number R, and if that is beta is bigger or same than every x element of x, then we will call beta as upper bound. And there will be upper bound region, same as there will be bounded, set f will be bounded below if there is lower bound. It is not guaranteed that bedtime alpha exists. Yeah, it's not guaranteed that we don't know there is real number alpha and beta exist. We can also write it like this. For all s.
um, so so I want to stop you right there. It's not guaranteed that alpha and beta exist. it's that it's not guaranteed that alpha and beta are within the set. Um, so like your upper bound and lower bound might not actually be within the set.
Uh, it is not maybe in a set, but it is like maybe it is out of the set, you mean?
Right. So an example would be like the interval
Mm-hmm.
um, from -1 to 1,
Mm.
non-inclusive.
Uh,
Um, so your lower bound would be -1, your upper bound would be 1, but neither would be within that interval.
uh, if it is kind of what function would be just like this function, which is mm, wait a minute, this is not a good example, I guess.
Typically, the way you would write that would be with the tip. So if you have the
Minus.
square brackets on an interval, that means it includes the endpoints.
Mm,
If you have the normal parentheses, that means it does not include the endpoints for interval notation.
mm,
So -1 to 1 non-inclusive would just be parenthesis -1 comma 1 parenthesis.
mm,
And in that case, neither your greatest lower bound or your least upper bound would be within the set S.
Yeah, this will be nice example. -1 to 1.
Hmm. Yeah, that's another way to write it.
Thank you for correction. And we are studying mathematics, so it would be very important to why it's still we should remember this notation for all x, which is element of S. If there's real number beta, then we will say there is upper bound. And if a is smaller than every x, then we will say there is lower bound. Empty set is bounded because we can write like this. Well, beta is bigger or same than every x, and a is smaller or same with every x. Upper bound and lower bound may not be unique. Yeah, in this may have multiple upper bounds and multiple lower bounds. This is kind of interesting. What kind of example can be exist? I think I should think about this. Jonathan, can you think about any examples that there is multiple upper bound and multiple lower bound? Multiple means
Mm,
there's more numbers.
yeah,
Yeah, right,
so
right, right. I was confused. Like this, there will be minimum upper bound, and
mm,
everything will be can be upper bound.
right, right.
Okay, let's go. I was a bit confused this part. And because of this, I think it would be nice we can remember this regarding lower bound and maximum upper bound, maximum lower bound thing. Okay, let's go. Show that A, which is 1 minus 1 over n, has an upper bound and lower bound. If we put n equals to from 1 to n, then we can get this. Let x, which is element of A, then x equals to 1 minus 1 over n. Then 1 minus 1 over n, this equa not equation, this property will be accomplished, hold, then we can get x is smaller or same than 1. Hence 1 beyond upper bound. Also, 1 over 1 over is smaller or same than 1. So we can do -1, then we can get lower bound. Mm. Tobias, do you have any questions here?
Yeah, just one. So for the maximum lower bounds or minimum upper bounds, are they still part of the interval or are they the ones that are just outside?
Mm. There will be, there can be,
So
or
yeah, they can be or they cannot be. Like it it depends on the interval. It depends on the function, whether the it can go either way. Um, it's not a definite thing. Like it being the
So
least upper bound doesn't mean it's in the set, doesn't mean it's not in the set.
so if we have a interval from 0 where 0 is included and it goes up to 1 where 1 is not included. So
Mhm.
0.9999 and so on would still be in the set. Um,
Right.
um, so both of them, or the upper one would be the minimum upper bound, and the 0 would be the maximum lower bound still, even though one of them is in the set and the other one is not.
Correct.
Okay.
okay.
So just essentially these maximum lower bounds or minimum upper bounds just define the edges, I guess, with a rational or with a real number.
Mm. I'm
Mhm.
understanding it like that.
So yes, it gives you the boundary line between in the set and out of the set, but that boundary line is not necessarily in the set itself.
All right. Thanks.
For natural number n, uh, we can show there is no upper bound. Let's see how we prove it. Let's say there's b, which will be upper bound. Then b should be or bigger or same than n. But we can find n, which is actually bigger than b. So by contradiction, there's no upper bound in n. And we also consider the set a positive real number, which is whose squares are less than 2. A has lower bound 0. Prove that A does not have maximum element, which means same. We should show there is no upper bound. Let A is in A, then A square is smaller than 4. Then A is bounded above by 2. Suppose that P is maximum of A. But since P is in A, and P is bigger than 0, and P square is smaller than 2, hmm, yeah, it assumes P is maximum of A. And if we show 2 is bigger than P, then actually there is no upper bound. If we solve this, we claim that Q square is smaller than 2. So it exists, so there is no upper bound. Here we now prove up existence of 2. We can prove it by there exists x which is real number such that x squared is equals to 2. Then we can consider a set which is x squared is smaller than 2. Think we use completeness axiom. We don't learn completeness axiom yet. I will pass it right now. If I just try to understand it intuitionally, it is defining a number u, which is such like this. So, which consists with lambda. So we are showing lambda squared is smaller than 2. So u squared is smaller than 2. I think I should figure it out again. Why existence of root 2 can be proved by showing there's no upper bound, I guess. And now supremum and infimum come out, which is least upper bound and greatest lower bound. Supremum will be from the upper bound if there's minimum. U is any upper bound, and if there is B such that smaller than every upper bound, it will be primum, and there will be minimum, infimum, which is greater than any lower bound. It also, we didn't guarantee that primum and infimum is in set S, which is bounded set. We can write it like this. Or all upper bound, U is bigger or same than B. And there's unique about, we will talk about uniqueness of primum. It should hold one of 3 conditions. By definition, A equals to B. And we'll say if S is unbounded above, primum S would be infinite. Its first part, we are going to infinity. And there is property for primum. If lambda is primum of F, then for every epsilon, some epsilon S, there is some x epsilon which is smaller or same than lambda, and bigger than lambda minus epsilon. What this is talking about is we can choose some real number between primum and not a primum thing. That is, I guess, what it is talking about.
Yeah, so to clarify on that last one, because that last one is really, really important. What that's saying is if you have your least upper bound for any value epsilon, any real value or any value epsilon you can pick, there is a value within your set that is between your least upper bound and your least upper bound minus epsilon. And that holds true for any value of epsilon. So no matter how small of a value you pick, there is always a element of that set that is within that value of your least upper bound. Same holds true for greatest lower bound as well.
We can say it's
And that's important.
kind of
What were you gonna say?
we can say it's kind of proposition that shows the density of real number.
Yeah. Yeah.
Okay. For proof, I will make it as exercise. Exercise. Lift upper bound property of real number. Every non-empty subset of R is bounded above has the primum in R. And we went to well-ordering principle and mathematical induction. Every non-empty subset of F of n has at least element, which means this has some n which is in S such that all k is in S, which is k is bigger or same than n. In other words, if there is subset of S which is in natural number, then there is some n which is minimum of S. Mathematical induction is if one is in S, then by inductive that if there is n is S and n plus 1 is S, then S is equal to n. This is what mathematical induction shows. And these two are kind of related. Yeah, there is equivalence of mathematical well-ordering principle and induction. Because time is almost 12, I will cut it, and from next time we will talk about equivalence of well-ordering principle and induction and Archimedean principle. Is there any question from Tobias or Jonathan? Okay, thank you for joining today. I will stop my video.